Right, hello and welcome. This is a A2 Edexcel video on integration, volumes of revolution. Don't know, my mind was going there. Around the x-axis and around the y-axis. Now I haven't done these as separate videos because they're fairly easy and they're related. I'll point out a few bits that you can relate them together. Because once you know one, it is quite easy to do the other. There's a simple switch method. So in essence, you only really need to learn one method, and then you can just flip it over to the other axis. So if you learn the x-axis, you can just do a substitution in terms of you turn the x into a y in that case. To the y-axis. So anyway, that might have been a complete and utter bit of baffle, but the key thing is, even though it's volumes revolution around the x-axis and the y-axis, there's one method for both, but there's a slight change. But as I said, you don't need to worry about that too much. So what I'm going to do now is I'm going to try and scale. Not literally, I'm not going to rip off my face, or this face is probably scaring off, but anyway, so what I'm going to do is I'm just going to demonstrate what we mean by volumes revolution by the x-axis and around the y-axis. So I'm going to draw a standard graph here. Now, actually, in circles, board up, just change my mind. So sorry, yeah, the agenda. The agenda for this video, what I'm going to do is I'm just going to now demonstrate. I'm going to do a volume revolution around the x-axis and one around the y-axis, so you can see the difference between them. And obviously it sounds obvious, but just for those people who don't get it doesn't sound obvious too, because obviously it's not going to sound obvious to everyone. It's obvious, isn't it? Anyway, so as I said, what I'm going to do is I'm just going to demonstrate the two differences, what x-axis around the x-axis look like and what around the y-axis look like. I know obviously when I was learning this all them decades ago, I was a bit stupid. It didn't come to me straight away. So don't feel bad. It was obviously pretty smart. Anyway, so we'll go through them two facts and then just go through a few questions. I'll go through these two and so that around the x, around the y-axis, state the formulas, and then we'll do some questions. I'll sort of split the board up again so we can apply this knowledge we're going to do now into some questions. Okay, so first of all, so what we need is a graph. And I'm still in economics mode of drawing proper axes, but say maths, you've got your x and your y. So if I just draw these axes on. So if they're not perfect, I'm just gonna... Right, okay, so there are two axes there. Now, the curve I'm going to replicate round the x-axis it's just a curve. It's just y equals the f of x. Y equals a function of x. Okay, so that's sort of, should have drawn it in a different colour actually. Got all these different colours and I still use one colour. Right, one sec, I'll just redraw that with a different colour so it's a bit more obvious. Oh, great. You know what, I'll redraw the whole thing and then I'll probably end up waffling on. Okay. So if you saw that, great, otherwise I'll just draw it again. Because I don't think it was that clear. Draw that again. It's going to look something like... If that's a bit clear. Unclear? So that's going to be... We're going to rotate this around the x-axis. And this one, we're going to rotate around the y-axis. Now for this purpose, I'm going to draw y equals x cubed. But I'm only going to draw it in the positive sense of y. So where y is bigger than or equal to 0. Just for simplicity. So it looks something like this. So if you were to draw the other bit, go down there. But as I said, I'm just focusing on the positive y-axis just to make it simple. Now obviously you would have limits in terms of when you actually do these questions, but just for simplicity I'm just going to demonstrate what it looks like. So here we're going to draw the same axes again. Stop putting a pen down, picking it up again. So we've got the y-axis and then we've got the x-axis as normal. But what we're doing is we've got a line here. This is 2D at the moment. This is just a curve. But if you were to rotate that curve, basically what we're doing is we're turning these shapes into 3D. So we're turning them into sort of a sphere, cube sort of thing. Not sphere, cube, sphere, circle sort of thing. So basically what we're doing, it's quite hard to show on a 2D whiteboard, but we're sort of rotating this, we're bringing it all the way around. We're sort of pulling it and pulling and twisting it around, and keep on extending this graph. So it's going to look something like this. So my drawing skills aren't brilliant, by the way, so I do apologise. So it's going to look something like that. Now obviously, as it said, my drawing skills aren't brilliant, but the drawing isn't the main part of it here. That's actually quite alright. So hopefully, just check, you can see that it looks something like that. Basically, we've rotated it around the y-axis, the x-axis on that. It's not good if I can't even remember what I did. And then for this one, which is obviously y equals x cubed, but we've only done it in the positive y sense. So we've got y, and then we've got x. So we've got this. Now, same principle, except we're not... Actually, a good way to think of this, just popped into my head, is you can think of this as wrapping the line around the x-axis. So it's doing that. So if you've got the x-axis... Oh, this is going to look really wrong for some people. But if you've got the x-axis here, it's going around... I don't know if that will work, actually. It's going around it, around the x-axis, yes? And it's not going... So if we've got the x and the y here, it's a bit of a more 3D one. So this is, you're looking directly at the x-axis, is this. And then this green pen is meant to be the y-axis. On the other ones, we've wrapped it around. This really isn't going as well as I thought it would. We're actually going around this x-axis, but on this one, on the y-axis, we're wrapping it around the y-axis. So we're going all the way around this. So if you're looking at it from, so if I'll turn it around, it's going round the green pen. Whereas on the x-axis it was going around, sort of looping over it in a big sort of circular motion thing. Whereas on the y-axis it's going around it on the top. So hopefully, as I said, if that looked weird, or if it didn't make any sense at all, don't worry, because I didn't know where I was going with that, but hopefully demonstrate something. So anyway, using that method, there was a method, you would get something that looks like this. So as I said, wrapping it around. And they're not too bothered, really, as long as it looks like you've done it around the y-axis. And obviously you'd be given limits, as I said. You might have, say, integrated between y equals 8 and y equals 2, for example. You should cut it off there. And then you just carry on the curve. Now, actually, it's a good point. So, when it says integrate between 2 points, obviously it won't be integrating the entire curve, which is what it's done here. But what about if the curve it gave us in the range of 0 to 9, it said rotate this curve around the x-axis? Well, it wouldn't. It'd say integrate it between these 2 points, which you'd know to wrap it around the x-axis. How would you draw the rest of the curve? You wouldn't get any marks for it, but just how would it look? Well, it would sort of continue. So if it's going down, it's just that given range that is wrapped around the x-axis. You don't need to wrap any excess. So when it says integrate between these 2 points, you don't need to wrap the rest of it around the x-axis. You just simply, I know it's a little bit too simple for some people, but you only rotate, you only draw, well, crudely draw in my case, the bit around the x-axis or the y-axis in the range it wants you to, not the range of the whole curve. I mean, as I said, you won't lose any marks for that, but just when you're working out, it might help you to understand. Because if you draw, now if you just draw the rotation around the y-axis, the whole curve, you might just not read the question. I know I would, and end up integrating the whole thing, which is just pointless because you'd obviously get the wrong answer. Now, very good that we have them curves on the board there. So as I said, you rewind that if you didn't catch them. But how does that actually help us? I mean, it's a integrate between these 2 points with reference to the shapes. So, very good, we can draw the shapes, well done, but that isn't math. Math doesn't work like that. Math just likes to be awkward, just like me. So that's why I get along with it. Now, to understand this, we need to remember. Sorry, I'm just missing. Sure, slipping out. So equation for it. Yeah, we need to memorise the equation of a cone, which is a third pi r squared times h. Sorry, I was just looking for that. Third pi r squared times h, which is what was on, not what was on the board, but that was the shape that was on the board. So you'd integrate. So we'd have to relate that somehow to our formulas. Now, I'm just going to give you the formulas actually straight away. You don't need to know, as I said, I did try to give you a little bit of an explanation there. It wasn't a brilliant attempt because I don't want to focus too much time on it. But basically you just apply that the third pi r squared times h to the equation of the curve and integrate it as such between them 2 points. But I don't want to confuse you too much because I already feel I'm starting to confuse you a little bit. Well, for them people, I'm confusing myself anyway. So, right. Just going to give you the formulas that you need to know. Now, the formulas you need to know is for the x-axis, it's the integral of pi. Oh, sorry. The integral here, I'm just going to write on these. Because obviously you will be asked to integrate by 2 points. Generally, you won't just be asked to integrate. You obviously get your limits a and b, and that you will be integrating pi times. Now, if it's around the x-axis, you use y squared because y squared equals the function of x. So, if you're integrating around the x-axis, this makes sense. Then you use the y coordinates because you're going over the y coordinates. So when we use that example of the 2 pens, this is going to change it to blue just to confuse you. But when we're wrapping it round the x-axis, yeah, very good. We're wrapping it round the x-axis, but we're actually going in accordance. So if you look at it from this angle, we're actually going in accordance from the y axis. So this going up, this motion with my finger, just don't pay attention to it. We're actually going over. These are y coordinates as well as that. This isn't really an invisible x coordinate. So we're going round the y coordinate. So we're having a change of y. It's y squared to be precise, because well, don't need to go into too much detail. But anyway, the point is when you're integrating on the x-axis, you're using the y coordinates because you're going around, up and down, so through positive and negative y coordinates. So you need to square them. So therefore, it's pi times y squared. This is with, in the case of when you're rotating around the x-axis. And now, when you put y squared, so y equals a function of x. So this y squared could be x take 1 squared, which you're going to have functions of x. And then if it's got functions of x and you're integrating it, you need to integrate it with respect to x. That's why you put dx there. Similarly, if you were integrating the y-axis, because the y-axis, so this is the y-axis here, and you've got your x-axis going across it, sort of cutting like, oh God. This attempt is really not going very well, but I'm going to continue with it anyway because I'm awkward. So we've got our x-axis and our y-axis going up there. When we were integrating around the x-axis, we were going over the positive and negative y coordinates, whereas, because obviously it's going to be equal on both sides. When we're going over the y coordinates though, so this is still the x-axis, I've just moved it to what it normally looks like on the board in terms of a graph, we're actually wrapping it around this bit, the top bit. So if I turn This isn't very well at all. But if I turn it like that, so this is the x-axis, but we're just looking at it horizontally, vertically from the top of the y-axis. This is the y-axis. When we wrap it round the y-axis, we're going through positive and negative x coordinates. So therefore, when we wrap it round the y-axis, we're going over positive and negative x coordinates. I said that twice, but never mind. I was trying to explain. They're going through positive and negative x coordinates when you're wrapping it around the y-axis. So it has to be x squared, not y squared. Because when you're wrapping it around the y-axis, you can't be changing y coordinates. Because otherwise you'd have some kind of squiggly thing when you're wrapping it around. Because it has to be a perfect sphere. You have to wrap it perfectly around the y-axis. So you have to be changing the x coordinates. So that's why when we wrap it around, obviously there's some maths behind it. But that's the way you're thinking about it anyway. So we've got the same limits a and b. So it's pi times x squared with respect to y. Because when it's y equals x take 1, is x equals y plus 1. Obviously, simple rearrangement. That curve was a complete and utter just made up curve. So therefore, when we put x, so x equals something, it's going to be x equals possibly a number, a coefficient with y. So there's going to have y's in there. So if we're going to have to integrate something with y's in it, we're going to have to integrate it with respect to y. So that's why when we put y squared, when we do the integral of the y-axis, we put x squared with respect to y, because obviously it's going to have y's in it and not x's, because we rearrange the curve. Similarly, when we wrap it around the x-axis, we use y squared because we're going over the y coordinates. And because we're putting in y is equal to something, it's going to be y is equal to a function of x. That's why y equals f of x is the same thing. So that's why, because then we have x's in it and we have to integrate with respect to x. Now, a key thing I would stress at this point, when you get to do these equations, it's not pi times y squared and the integral of that, because obviously you can't integrate y with respect to x unless you change it about, which would just be a nightmare. So the thing to do, I don't think that, is you go pi times the integral of a and b with respect to y squared with respect to x, sorry. And similarly, it's going to be your pi times your a roots limits of a and b x squared with respect to y for your y-axis. So you could actually think of it as whatever here, because I mean it won't give you these equations, but whatever is here, so whatever you're integrating with respect to, that's what you're rotating it around. I mean obviously it'll, as I say obviously, because they won't give you that and say, oh, use that, and they won't tell you, they will tell you what to wrap it around, but just for your mind, you know which equation goes with what. Because having y squared and having that flip round, wrap around the x-axis, sorry, rotated around, it is a little bit confusing. Why would you use y? But I tried to explain it in the least mathematical sense, but the logical sense of what possible. So as I said, they're the two functions, and it will become a lot clearer. That to some of you that might look a little bit weird, but you know it really isn't that bad. So what we're going to do now is I'm going to leave them on the board. I'm going to split the board up into two sections. And so you're going to move these, just rewrite these equations. So I'll organise the board a little bit better. So give me a second. I'm going to use red to split it up. You know, because obviously that's the best colour in the world. Which obviously it isn't, but you know. So anyway, I'm going to write on the right hand side of the board, I'm going to write my equation for my volumes of revolution around the y-axis. Now this volumes of revolution, it's not just flips around the x-axis or flips around the y-axis, but I just try to keep it nice and simple. And then just write the equation for integrating around the x-axis, which is y squared with respect to x. Now, as I said, your y squared, if it's 1 take x, you don't just square 1 and square x, you do standard double bracket thing, but obviously you know that. So we're going to do a few questions now. Just going to cordon that off so we don't get our things mixed up with our equations. Now, actually, just for those of you that sometimes don't pay attention, because I do waffle on a bit. So that is rotation around the y-axis, and this is rotations around the x-axis, because you remember we've got respect to x in there. And obviously you don't have two equations with the same axis, so you've got a 50% chance of getting it right anyway. So anyway, I think they're in the formula, but I personally advise learning them, as they are they are the foundations of this topic, and what this whole topic's about. Now, what I'm going to do is I'm not going to focus on the y-axis straight away. Actually, I'm going to focus on the x-axis, and that's because there's a couple of key things that we need to know. The y-axis is fairly simple. In terms of, once you know the x-axis, you can just apply that to the y-axis, as we've said before. But the x-axis, sometimes, if you cast your minds back, when we did in C2, we didn't do volumes revolution, obviously, because it was a little bit complicated. But what we did was we did when we integrated to find the area between two curves. That's why we're integrating the rotations, because the area of these rotations. When we integrated curves that had the area between them, we always did the integral of the one on top, and then we found the limits of the intersection, and then we took that away from the integral of the curve on the bottom with respect to the integration. So we do apply this theorem to this C4 topic of volumes of revolution when we have two curves for the rotations around the x-axis. But I'll explain a bit more about that. But that was just how C2 links into this. But I'm waffling on. We do need to actually be able to understand what we mean by this rotations around the x-axis here. So one sec, I'm just going to pick a question, because I thought I picked one, but obviously it's not good enough. One sec. Right, so hello, welcome back. I've chosen a question now. So, just draw the curve. Oh, so I can't put y there. Dear me. So the curve looks something like this. And we are told the equation of the curve is y equals 3, that's right, over the square root of 1 plus 4x. Now obviously you know that's 3 over the 1 plus 4x to the power of a half, which is also equal to 3 brackets 1 plus 4x to the power of minus a half, because of the reciprocal factor there. So hopefully, as I said, it's making a fair amount of sense so far. And we are asked to integrate this curve, find the area between x is 2 and x is 0. Now this shouldn't be too much of a problem, because we're not flipping it around just yet. All we're asking to do is integrate, find the area of that little bit there. So all we're doing literally is integrating as we did in C2, with your limits of a and b being 2 and 0 respectively. And then we're saying integrate the brackets of 3 plus 1, sorry, 3 brackets 1 plus 4x to the power of negative half with respect to x. Now, it's going to be quite difficult to do that. So what we need to cast our minds back, we need to cast our minds back to something called the reverse bracket rule of integration, which stated that to integrate ax plus b to the power n, what you needed to do was you needed to raise the power by 1, so ax plus b to the power of n plus 1 over that n plus 1 times 1 over a being the coefficient of x, and then you add c on to the end of that. Now we've got a little bit of a problem here because this is 3 times this, whereas what we do, don't need to do anything really in terms of additional mass. We just need to bring the 3 in front of the integral because we're not integrating the 3, we're not bothered about that. 2 and 0, and that's the 1 plus 4x all to the power of negative a half with respect to x. So now it looks exactly like the method that we have below, which means, joy of joys, we can do some maths with this. So if we follow the exact same formula for this as for this equation, as we did as the formula states. So this says that is equal to the ax plus b raised to the power by 1. So if you raise the power by 1 of, so I'll put it in the same format, I'll just rearrange it. So 4x plus 1 instead of 1 plus 4x. 1 plus a negative a half is obviously a half, over 1 plus negative a half, which is a half, should be said, times 1 over a being 4, so that's 1 over your 4, plus c. Now you don't really need to include that because when we integrate it, c is just a numerical answer, it's just a coefficient of, it's not a coefficient of x, sorry, so it is, doesn't matter. So if we simplify this down, so that says it's 4x plus 1, power over half, over, it's not over half because a half times a quarter is, 4x plus 1 to the power of a half over a half times a quarter is 4x plus 1 to the power of a half on top, over, we times the numerator and the denominators together, 4 times a half is 2, and that's your answer there. Now that is not your full answer, that's just your answer to your integral. We still need to integrate this between the limits of 2 and 0. So all we do, therefore, is after this we sub in x is 2 and take that away from x when you sub in x is 0. So this is just like any other C2 equation. So it's 4 times 2, which is obviously 8, but I'm going to leave it as 4 brackets 2, plus 1, and then you square root that, over 2 plus, take away. Sorry for my terrible handwriting, I'm kind of writing on the side so it's not taking too much of the board. 4 times 0, which is obviously 0, plus 1, and we square root that whole answer, which is obviously going to be 1, over 2, and then we take them two answers away. So if I just explain this 3, so 4 times 2 is 8, plus 1 is 9, square root of 9, obviously 3 over 2, and then, so 3 over 2, take away something, so this is 1, square root of 1, which is obviously 1, over 2, so 3 over 2, take a half, which, so if I write that in numerical form, so 3 over 2, so 1.5, take what, 0.5 is 1, so that's 2 over 2, which equals 1. Now it's not 1, it's 1 units cubed, because, units squared, because we're talking about area. So that's your answer. Oh, sorry, that's not all of it. Now that'd be the answer if it was 1 plus 4x to the negative half, but it's 3 times 1 plus 4x to the negative half. So what we need to do is times our final answer by 3. So it's not 1 unit squared, it's 3 units squared. And just got cut out there. Sorry about that. So that just points out some of the things you can miss. Now I could have kept that 3 in there, but I thought we muddled it up, but I ended up muddling myself up anyway. So that's the correct answer now, it's 3 units squared. And it's unit squared because it's 2D. When we turn it into 3D and we start using it, these revolutions, we've not used these equations yet, by the way. All I've done is use a reverse bracket rule of integration, which in your books is, I think, chapter 4, and we just applied it to this case. So it's just a sort of more of a recap on what you should already know from C4. So as I said, nothing too strenuous. We're going to get back into our new theory today of volumes of revolution with sticking with this idea. Now hopefully, as I said, just come around and make sure you can actually see that. What we're going to do is we're going to use this example again, but we're going to rotate it around the x-axis. So I'm going to rub all this maths out because hopefully you've had a chance to copy that down. So we're going to stick with the same equation for the curve, but this time I'm going to rotate it around the x-axis by 360 degrees for rotation, which means obviously we're going to be using that one over there. So if we draw the graph again, but this time instead of 2D, because that'd be pointless, it's because we've already drawn it. I'm going to draw it in 3D because that's the rotation around the x-axis. So a way of showing it anyway. So it should sort of look like this. Really sorry for my pitiful drawings. Where's it gone over there? Sorry. Irritates me if it isn't okay. And then obviously your line will continue, but we're not really interested in that. We're interested in this bit between x equals 2 and x equals 0. So they're the 2 points that we've been asked to integrate between. So you should know that the integral of this, because we did it in the last video, we did, sorry, not last video, last question, we integrated that equation and we got 3 over 2. Sorry, I'm having to refer to my notes because I don't want to say something that we didn't come up with. So 3 over 2 brackets 1 plus 4x to the power of a half. So that's what we got when we integrated that equation as we did before using the reverse bracket rule of integration. So we don't need to do any of that yet. Now, what I normally do, obviously I wouldn't have these rules at the start of the page for every page that I did in the exam. So what I do now is I write out this rule. So I'm going to do it even though we've got it at the top, just for purpose. But I'm going to be subbing in our y equation here. Now remember, this is the integrated equation of y. So we're not going to be integrating this equation. Sorry, I meant this one. My finger wasn't pointing in the right sense. So anyway, let's crack on with this. So if I write the simple equation, so I'm confusing myself here. So if we're just writing y, just simply rewrite this in substitution with our original curve. And we know our limits are 2 and 0, and we're integrating pi times y squared, which is, if we open brackets this, it's 3 open brackets 1 plus 4x to the negative a half, and that is all squared. So then if we expand this out, so I just give you a second to copy that down. So obviously before we expand it, sorry, just to simplify this down, it'd be pi times the integral with the limits 2 and 0 of 3 over. Actually, I've just checked my notes and what I did, which I actually think makes more sense. It's 3 over 1 plus 4x, or 1 plus the root of 1 plus 4x, square root, because it makes it easier to square. So then what we do is we square 3 over 1 plus 4x to the power of a half, and then that gets us, so that continue, so it's pi times the integral, because y squared, not y, 2 and 0. So 3 squared is obviously 9 over, now it's not 1 plus 4x is a half, because a half times a half, when we're times in powers, when we're multiplying, when we've got power outside the bracket, we times it by power inside the brackets, we are multiplying powers. So that means it's just over 1 plus 4x. So to integrate this, we use the same method as we did for up here when we integrated the original equation, but obviously this time we've got a little bit more to do. Now I'm going to rewrite this in a simpler form before I integrate it. So it's pi times the integral to 0, sorry, there the limit's to 0, of 9, 1 plus 4x to the minus 1. So, use the same method that we did. So I'll just remind you of the method. The method was the integral of ax plus b to the power n equals ax plus b to the power of n plus 1, we raise the power by 1, over n plus 1 times 1 over a plus c. So if we did the same idea with this, so we'll leave the pi outside the brackets, so it's pi times, and I'm going to open some square brackets because we don't need the integral sign anymore. So that could be 9 pi, by the way, because we take the 9 out of the equation. Obviously 9 times pi, or 9 pi, whatever you want to say. So we integrate just 1 plus 4x to the minus 1. So as we're following this method up here, 1 plus 4x, now it's not the minus 1 on top, it's 1 plus 4x to just the power of 1, which is just 1 plus 4x, but I'll put the 1 there so you know what I'm doing, over 1, because that's minus 1 plus 1. Is that right? Sorry, just do some basic math on there. Yeah. One sec, just just need to check this. I've done something wrong, but make sure. Sorry, I just remembered I missed quite an obvious rule here. Right, so ignore that little bit there. Now, what this, a good way to look at this actually, sorry, it's 9 times 1 over 1 plus 4x. Now, so then it's 9 pi times the integral of 1 over 1 plus 4x. So anyway, what we were saying is, just before I peeled off to have another check on my workings, this 1 over 4x, or 4x, 1 plus 4x to the power of minus 1, that is the derivative of ln of x of 1 plus 4x. But it's not just the derivative of that. Now the reason is, because when you do the derivative of ln of x, you do the f dash of x, sorry, yeah, the f dash, or the derivative of what's inside what's being ln'd over what is actually being ln'd. So it's f dash of x over f of x, and when you integrate that, because that's the differential of ln of x, and remember then and integrals work in opposite ways, so we've got the ln here, we differentiated it to get 1 over 1 plus 4x, and then we integrate that to get the original ln of x. But it's not just ln of x, because that isn't f dash of x over x, it's f dash of, it's something. So basically it's the derivative of 1 plus 4x is 4, and that's 1, and the derivative of 1 plus 4x is 4. So to make this equal, we need to we need to get rid of this 4, so we turn it into a 1, because that's what's on top of this equation. We need to times 4 by a quarter to reduce it to 1, which is what's on the top. So therefore the integral of 1 over 1 plus 4x is actually, so if we expand this out, 9 pi times the integral of 1 over 1 plus 4x. So it's a quarter, so 9 pi times a quarter of, or a quarter times the ln of 1 plus 4x. And you could add c onto that. So that's what it is. That's what bit I was missing out there, because I was going to raise the power of minus 1, thinking, oh, it's 0. 0 is 1, so what am I going on about? So anyway, that's hopefully makes some kind of sense. Yeah, so as I said, hopefully that makes some kind of logical sense. that's actually quite a good thing to point out at this stage, because most people would, including me actually, I did miss that out, so I had to recheck what I did. Whenever you do something to the power of -1, it's the differential, and it's over that. So you have to relate to the ln of x, because this reverse bracket rule of integration and your integrals of ln of x are topics that we've previously studied in C4, and we're applying them to this very case of volumes of revolution. So that's why C4 is quite difficult. But as I said, hopefully it's nothing too bad. So that's just that's the integral answer. So we could get rid of the plus c, because we don't really need that, but it is good to have it down and know that you need it there. So therefore it is your answer is going to be, because that's 9 times pi times a quarter of ln of x plus ln of 1 plus 4x. We could do pi times 9 over 9 quarters times the ln of x of ln of 1 plus 4x, but we just leave it as that, and then we need to put back in our limits of 2 and 0, and then we would just simply sub it in as per normal. So 9 pi times, obviously you could do the 9 pi afterwards, but I'm going to just leave it in, times a quarter of ln of 1 plus 4x, and x in this case being 2. So 1 plus 4 times 2 is 1 plus 8, which is 9, so the ln of 9. Take away 9 pi times a quarter times the ln of 1 plus 4x, and 0 being x, so it's just 1 plus 0 or 1, and then that should get you your answer of actually you couldn't really simplify it. You can just leave it as that if you would like, or you put that into your calculation depending on what kind of form it asked you. But for this question it doesn't specify, so you can just leave it as that. So anyway, hopefully that made some kind of sense. As I said, that was quite a difficult one. That was an exam question from some given year. I'm not sure, I wouldn't have liked to see that one in an exam, but as you can see, the level of difficulty here is quite high. Now, that's not even as bad as it gets, actually. So, as I said, hopefully that's made sense. All we did in that question is we just integrated using our using our reverse bracket rule of integration, and we subbed in our values there, and we just used our integrating of ln's, which was a nice hidden thing for us to find. So what I'm going to do now is right, hello, welcome. This is the question I picked. So basically it says integrate. So find this area R that has been rotated around the x-axis by 360 degrees. Now, first of all, a couple of things that we can't do at the moment. We don't know this point x2. We know the point x1, which is obviously 0, because it says x has to be greater than 0. So obviously one of the intercepts is at 0. By just working it out, we've got y equals x over 3 and y equals root x. Now, to find this point of intersection here, we need to let y equal y, so obviously that is quite simple. So it's x over 3 equals root x. So then if we times both sides by 3, so that x equals 3 root x, square both sides, so x squared equals 9x. Now, what you might be tempted to do there is divide both sides by x, which wouldn't be a good idea if you lose one of the answers, but hopefully you can understand. So x squared, take 9x equals 0, factorise that, so take x out as a common factor, so that's x brackets x, take 9, and that's equal to 0. So therefore, your two x values are x equals 0 and x equals 9. And obviously, we've got 0 here, so this x2 must have an x value of 9. Now what we could do is we could find the coordinates of that. We could go, yeah, x equals 9, so y equals x over 3. We'll put 9 over 3 to get y is equal to 3 at that point. And vice versa, we could also do it as root x, root 9 is 3. So shows that her coordinate is both. So that would show both, sorry. So right, that's okay, but we don't need the y coordinate. This is one of them equations, them times in maths, one of the very few times where you don't need both points of intersection. You don't need your x and y points, although it does, it doesn't really ask you to do as such. So anyway, that's part of the question. So we know what the intersection is. So therefore, our limits are going to be 0 and 9. So our a and b values are going to be 0, 9. So a is equal to 9 and b is equal to 0. So just like we had up here in our little thing up here, a is 9 and b is 0. So that's what we're integrating between. Okay. So hopefully that's making some kind of sense. Now, as it said, so as it says, we have to rotate this around the x-axis by 360 degrees. Now, what we did before is we took we did the integral of the curve on top and took that away from the integral of the curve on the bottom, because the integral of r between these 2 points would give us the integral of all of between 9 and 0, and then the integral of x and 3 will give us all the area below the curve of y equals x over 3 between x is 9 and x is 0, which is exactly what we do. But to put it into perspective of why we do that and how it still applies when we rotate it, we need to first of all draw this rotation. So let's apply this theory. So we've got y equals x over 3 and we've got this little area here. So it's going to look, sorry, try to do that without the notes. So let me perfect this. Great, it's going to irritate me. As I said, sorry if it's not perfect. Great. But as I said, the shape doesn't really, it's not the maths that matters, but the shape irritates me if I don't get it right. So you don't need to worry if this shape doesn't look perfect. And apart from the fact that I would hate for the shape not to be correct. Although I have a strong feeling I'm going to mess it up. Anyway. Yeah, I messed that up. But hopefully it's reminiscent of something that looks like it. So that's something that would, great, so it goes off there. So hopefully that looks like something reminiscent of the point of intersection there. So you've got your y equals x over 3 curve continuing and your y equals root x sort of bending over as we had in that situation. So that's what it kind of looks like. As I said, the situation, the sketch isn't that important, but it's just to visualise it. But as I said, I'm not very good at that. So anyway, that's the sketch. That's what it looks like. Now this y equals root x here, because it's on top, is actually this bit. Wait, it picked up that same colour. Pick up a different colour for once. Let's pick up the same colours. So it's black or blue. No, we'll go with green. Go back to green. This y equals root x is actually the outside bit. So that y equals root x, that's the outside bit because it's on top, so it's over the other one. Now the y equals root x is the y equals x over 3. This is actually the bit inside the little rotation thing. So the integral of y equals root x plus the integral of y equals x over 3 makes up this whole cylinder and fills the hole in there. So there's nothing, so it's just a sphere sort of, an elongated sphere. But obviously that's not what we want, because we want the area of the outside. So the best way of thinking, right, if that doesn't make any sense, is we've just rotated we've rotated y equals root x over in a revolution around the x-axis 360 degrees, and we've rotated y equals root x over 3 around the same way. But we still apply our C2 to things of you integrate the curve on top and take away from the integral of the curve on the bottom, because we've got our limits of 9 and 0, which you can put back on. x2 equals 9, x1 equals 0. So we can put our limits back on, and then we've got something reminiscent of what we should have. Okay, so hopefully that makes some kind of sense. Right, let's continue with the rest of this. Right, so what we need to do now, that's what the curve looks like. We actually need to integrate these two curves. And we have to use one of these methods, and because we're rotating around the x-axis, we have to use the one with the y in it, which is this pi times y squared with respect to x, because we're rotating around the x-axis obviously. So the way to do this is to integrate the individual curves. So you could draw another two diagrams, but A, I don't have the space, and B, I don't have the time for my life to do that. So remember, it's between 9 and 0, and it's the integral of pi times root x squared with respect to x. Remember, we bring the pi in front of the integral sign. Sorry, so that becomes pi times the integral with limits 9 and 0 of, now root x times root x is just x with respect to x. So therefore, it is pi times, if you integrate x, you get x squared over 2, or half times x squared, and same limits applied 9 and 0. You could work that one out if you wanted. Preferably I wouldn't at this stage, but I'll do it anyway. So it's pi times, so we just put 9 squared over 2, take 0 squared over 2. Now I'm not going to work that out, just leave it as like that so you could put an answer there if you wanted to. And then we need to take this answer away from the integral of 9, 0 pi times and the curve on the bottom, which is x over 3. Now it's not just x over 3, it's x over 3 all squared. So then do the same thing, take the pi out the integrals, so it's 9 and 0. Then if we expand that out, so it becomes x squared over 9, or a ninth times x squared. Sorry, that's with respect to x as well. And then we just do what we did before, square brackets. And that becomes x cubed over 27, because you raise the power, that becomes x cubed. So it's a ninth times x squared over 3. The 9 times 3 goes on the bottom, which becomes 27. And then we have the same limits as before of 2 and 0. So then we do the same thing. So we do pi times, we open these square brackets again, of your 2 cubed, it's actually 2 cubed. Oh, sorry, it's not 2. No, why did I put 2 in there? Sorry, it's between 9 and 0. Just create a, so it's 9 cubed over 27, take 0 cubed over 27. Now you could leave them zeros out, but I'm just doing it purely because that's what you would do if you had any other limits, and I'm not going to skip it out because it's quite a difficult topic. So then what you do is you'd work these two out and take them away from each other. So because that's the volume of revolution of the curve on top, take away the volume of the curve of the revolution on bottom, in terms of the order on this graph here, and you just work it out, and that gives you the area of this curve thing. So that's pi. So if we do this as a proper equation, so there's pi times 9 squared, which is 81. So it's 81 pi, or pi times 81 over 2, and obviously that's take away 0 squared, which is 0 over 2, which is 0, so it's irrelevant, that bit. So you take that away from, now your 9 cubed is 9 times 81, which is 729. Check me out. 729 pi, or pi 729, over, now it's not over 2, it's over 27. So therefore that's get you, if you cancel that down, just get you 27 pi, is it? Great, I thought I could do that without a calculator, but obviously it didn't work. Turn it. So it's 81 pi. Sorry. 81 pi over 2, take 729 pi. Should be right now. You might have to check my answer for that. Yep, that's 27 pi over 2, which is what I was expecting it to be. So 27 pi over 2, or 27 over 2 times pi. So that's, and now that's your answer, but it's not the correct answer because it's 27 pi over 2 units cubed, because it's a unit of revolution, so it's an area, so therefore that is equal to your R, or more precisely is equal to that area there. That's just, so it's more equal to the second one, but hopefully you can see I was trying to get them to say the same thing. Now that is quite difficult, I think you'll agree. There's a lot of maths on there. I don't think there's preferably that much. I think it is doable. But now we're just going to have a look at the volumes of revolution around the y-axis. So we're not out of the woods just yet, but that's quite a key thing. So I'll just give you a minute actually to copy that information down, and then we can get onto the y-axis. So just give you a minute. Right. Now we're going to do a question on rotation around the y-axis. Now we are told in this question that the graph that we are going to rotate around the y-axis, so obviously now we are going to be looking at this equation. This is useless. The equation of the curve is y equals 1 plus x squared. So therefore we're not told that yet. We're told that x must be bigger or equal to 0. So it gives us a bit of this help. And it says between the lines y equals 4 and y equals 0, which are just the limits a and b, by the way. Now, to use this equation, even before we draw this graph, well actually no, draw the graph first, okay? So, what this graph is the graph of a quadratic, you should know from C1. So, it's going to look something like this. However, if you pay attention, it's 1 plus x squared. So the graph has been translated up 1 unit. Now, before we start drawing in this left-hand side, well, actually, in a marker, we are told x is greater or equal to 0. So it's not going to be anything over to the negative side. So it's going to be something like this. So it's y equals x squared plus 1. Now we are told it's rotated around the y-axis. So if we simply rotate this graph without doing any further maths, we'll just add that on there, and we rotate this around the y-axis. Sorry, I'll move out of the way in a minute. We should have something like that, with the lines y equals 4, cutting the top of it and it continuing off, and y equals 0 going along the x-axis. So it should look something like that. So as you can see, it's just simply rotated around the y-axis there. Right, so that's all very well and good, but let's get back to the maths. Now, you'll notice in the y equation we've got x. Now, we don't currently have x, we have y equals something. So, obvious thing to do, y equals x squared, convert it to x, so it's a subject, so x squared equals y take 1, square root that, so x equals the square root of y take 1. Put it into this formula, so we know the limits are not the x limits now, we're talking about y limits, which is 4 and 0, times the integral of pi times x squared, which x is the square root of y take 1. Now if we just simply move the pi out to the front, so pi times the integral of the limits 4 and 0 of the square root of y take 1 squared, so that's just going to be y take 1, and then we can integrate that as normal, so it's pi times, so integrate of y is y squared over 2. Now you should put the with respect to y, by the way, and then the integral of 1 with respect to y is just y, and then you still have the limits of 4 and 0. So then we simply put our numbers in, so it's pi times 4 squared over 4, over 2, take 4, and then you just do take 0. Expand this out, so what we've got is we have pi times 4 squared over 4, that's 8, no, 16 over 2, which is 8, 8 take 4, which is 4, so it's pi times 4, hence it is 4 pi units cubed, or 4 pi cubed units. That is your answer. So hopefully, as I said, that makes some kind of sense there. Nothing too strenuous, I don't think. Not too far away from what you've been doing in the X. So that is all of your knowledge of volumes of revolution all done. That's probably one of the longest videos I've ever done. I do think it's quite a difficult topic to get your head around, personally, because I'm so bad at drawing these diagrams. That's probably why it's taken so long. But three main things to take away from this video. Number one, the two equations. Well, actually, there's 4, but that first one wasn't really a point. You get given them anyway. For the rotating around, there's 4. Rotating around the x-axis. Sorry, you substitute in your values, and you just sort of wrap it around the x-axis, and you only do wrap it around the x-axis between the points it tells you to. When you're finding the area of a intersection, so the area between two curves, you do as you do in C2, where you did the area of the top curve, take away the area of the bottom curve, you use integration. But we use the integration formulas that we've done on the board for volumes of revolution. Then we do the similar sort of thing for the y-axis, but we rearrange the integral of pi times x squared rather than y squared for around the y-axis, because we're changing the x values when we rotate it around the y-axis, and then that gets us so we have to rearrange to get x for that, obviously, such as in this case. And the two lines of y, they're your limits, so you have a and b are y limits when you're rotating around the y-axis, as opposed to x limits when you're rotating around the x-axis, which hopefully should be y limits when you're doing the x limits when you're running the x-axis, which as I said, hopefully should be fairly self-explanatory. I'm guessing you would have already guessed that already. So as I said, they're the key bits really to take away from this video. There's not much more to it than that. That is a few key bits that I've left on the board for you there. So thanks for watching, and we shall see you in the next video.